recording going?
Yeah, recording in
Okay.
progress.
Yeah. Okay. So thank you all the people for coming. Today we have Giovanni Sambin from University of Padua, Italy, with his new with a talk on related to his new book, Positive Topology, a new practice in constructive mathematics. And with that, I give the word to you. Thank you. We're by the way, also we're very pleased that you decided to give a talk with us. Thank you.
Okay, no worry. It's a pleasure for me to have contact with Russian logicians and colleagues, and that's it. It's a pleasure for me. So the first picture is from Padua, where I lived most of my time and where I worked. And the next one, let me see. Yes, this one. No, this one is from Venice, where I am in this very moment. That is the entrance of Arsenal, the main thing in Venice which made the power of Venice, and it is just there. You can see the wall there. I don't know if you could see the walls like that. Anyway, but let's go to job. So this is the title, Dynamic View of Mathematics Focusing on the Continuum. The focus on the continuum is just a way to jump details of other things and rely on intuition. What is a dynamic view? The main thing is that mathematics is the result of human construction. Every piece of mathematics is a product of culture. This is the main view. Now, this is my view, and perhaps not many share it. So you can think of this lecture as an experiment. We see what it happens if we believe in this that I said, and then change step by step the mathematics consequently, so that it can really be seen as produced by humans, that I call dynamic. So let's go on. This is the book. We already spoke about it. You already mentioned it. It's something which contains all what I will say today, but in a different order and with a different stress. After the book is finished, I am getting more and more radical in my ideas. So now I would write it in a completely different way, but I agree there are no mistakes. After 2 years, I feel there are no mistakes. Simply, I would stress on different things or follow a different line of exposition. So, if you think that mathematics is a human product rather than dealing with independent truths, truths independent of humans, then it's better to speak about the information contained in every notion or every object and not of truth, because otherwise you fall into the idea that truth, the most common idea that truth is there, up there, it is given, and you have to accept it. While the main point in the dynamic view is that truth is what we achieve step by step from below. So let's see the primitive, how you would change just the basic notions of mathematics. First principle is that since we pass from truth to information and want to gather as much information as possible, then we must avoid standard principles that do not preserve information. And I will explain immediately what I mean. So one slogan is, if you want to be maximalist in conceptual distinctions, which we are going to do, you have to be minimalist in assumptions. Also, standard assumptions will not be, very common assumptions will not be accepted. So what is a set in this view? A set is a bunch of elements that you generate inductively using a finite number of rules. So it has a strong effective content or computational content. You're given the rules, the language in which those rules are written, a finite number of rules, so you have to exhibit them, and that is our notion of set. Since it is external to us, once you specify the language and the rules, it will be stable in time, and you can treat it almost as an object. Typical example, of course, is natural numbers, but we will see also lists of natural numbers are inductively generated, and so it's another example. We will distinguish set from collection. Sorry, I add here, if you have any questions, please interrupt me. It's better I speed up a little bit and rely on you to put questions if I am too obscure, rather than go slowly and give all details. So I will speed up, but you stop me and put questions if I'm not clear. So the main distinction is between set and collection. Collection, we don't have rules to generate elements. We only have a sufficient criterion to characterize its objects. We call them objects rather than elements. Typical example, the power of a set, the power of natural numbers in particular, that is the collection of all subsets. What is a subset? We see in a while. We have no induction. A collection, the notion of object of a collection could change tomorrow, because we only have a sufficient characterization and not a necessary criterion. To preserve the distinction between set and collection, namely the property of being inductively generated, a collection is not a set because it is not inductively generated. So since the typical example is the power of a set, we cannot assume the power of a set axiom, namely that whenever you have a set, also all its subsets form a set. This is something considered very trivial in standard axiomatic set theory. Here we just don't assume it, because we want to preserve the computational aspect of the notion of set. And I repeat, the computational aspect is in the fact that you give finite instructions to obtain all its elements.
Yeah, may I just question, if it's long discussion, we can, of course, but when you say something is inductively generated, right? Is it already assume some notion of natural number, or you're rather thinking of induction, something like in piano arithmetic? Or you just take, there is first step, second step, and that would mean that you have the standard natural numbers somehow.
Of course, you can reduce it to natural numbers if you assume them to be given. I rather look in the opposite direction. I assume inductive generation is clear, and I see it as applied to specific cases. I believe it is a human capacity to understand the following. You are given something, some objects are given, some elements are given, and some rules to obtain new elements from these are given. And it is a human capacity to understand that you can iterate this as many times as you
And when you say human capacity, that means that it's the same for all humans. It's could be probably different for apes, but it's something belongs to the species, but not to culture, not to individual human, just for all humans.
No, of course, this is a very hairy question. There are populations where they stop counting at 5 or so. Then I would say that they don't have the notion of inductive generation. But I believe even if you get one person of that culture and bring it to our culture, or just try to explain him or her, then sooner or later he understands. Because people, even what people we call primitive, are smart, because all humans have the possibility, I told you, of these capacities. Because an example is jokes. There are many jokes that are based on a repetition 3 times of something. The first 2 give the rule of inductive generation, and the third goes against the rule, and then you laugh. And this shows in very concrete terms that we, all us, have this capacity of understanding something in our mind, that it will follow a certain pattern. And this, I rely on this to when I explain what inductive generation means and to explain what a set is. And note that I don't need anything axiomatic here. I don't need axiomatic set theory.
Okay, thank you.
Is that enough? Good.
Yes. Thanks.
Okay, very good. We can talk more about it, of course. It's not trivial, but I hope it is clear. So the power set axiom is not assumed because we want to keep this property of being inductively generated, and the power of a set is not inductively generated by a standard diagonalization argument in the style of Cantor. Okay, so what is a subset? Another thing we have to preserve. So yes, we will see that we want to preserve that logic is different from computation. But first, let us see what is logic in common understanding. We all agree that a proposition is something that can be judged true. And here, I don't go more in detail. I follow more or less the Martin-Leff explanation of what a proposition is, which is more or less this very short line. And we see its characteristics. So it's not a formula in a fixed language. That's the main point. To preserve the distinction between exists and not for all not, we cannot have the law of excluded middle. So that's another common assumption that we cannot have, because we want to keep the distinction between if you prove exists, then you somehow must have an element, at least virtually, an element showing that what you declare to exist, which is not possible if you only have not for all not. I mentioned what happens. Okay. I mentioned logic is different from computation in our framework. The this means this is the main difference with respect to Martin-Lev type theory. In Martin-Lev type theory, proposition is the same as set, the so-called principle of proposition as set. It is not accepted here precisely because we want logic to be different from computation. So in particular, proposition is not given by giving all its proofs through an inductive generation, as it would be for elements of a set. Proper proposition is have quantifications only on sets, so it is very effective as a notion. And we have a distinction between this difference between logic and computations. Computation allows us to have two main distinctions. One is that between set and subset. A subset is a proper proposition with only one argument. So this means in particular that D subset does not mean that D is a set. Why? Because a proposition, a subset, does not give you the rules to obtain all its elements. You only have a criterion given by a property, given by the proposition with one argument, but you don't have any criterion to build its elements. What is an element of a proposition? Note that this epsilon in the first x in D is a little bit different from x in D here in the second occurrence. The big epsilon means being an element of a set. The small epsilon, which is closer to the Greek alphabet, means being an element of a subset. And being an element of a subset means precisely being an element of the environment, the domain of the set, and the fact that the property is true on that element. Note that the two epsilon are different, and this distinction allows us to keep the effective notion of set and still have a notion of arbitrary subset that are always definable because being constructive, we want everything to be constructed. So the construction of a subset is just giving the property. And it's not construction in the sense of inductive generation, it's construction in the sense that we have the property characterizing that subset within a given domain. A relation is just a proposition with two arguments. So a proper proposition. So this allows to have the second main distinction between function and operation. It's very unfortunate that function and operation have, so the notion of function has two different interpretations in the classical and in the constructive view. But they are reflected in this distinction that we are doing in this moment, namely between function and operation. A function is just a total single-valued relation, and you do not require any information on how to get the unique value. An operation is sorry, this must be, that's the first mistake. Total single-valued relation is wrong. There you just delete that. Operation means specific instruction must be given to get the value. And the difference between the two is killed by the axiom of choice. Even the so-called axiom of unique choice, we will come back to this later. To see a better example, to see a good example clarifying and understanding better. more general distinctions are idealization is different from abstraction. This also will be discussed later. And truth is different from consistency. In particular, if something exists, does not mean that its existence is consistent, like an axiomatic system, but we must construct it. Okay, this is I will go very quickly here. This is an example of one question could be, can you do mathematics with a so weak system? You don't have law of excluded middle, so you are intuitionistic, predicative because power set is not allowed, and effective because axiom of choice is not allowed. Can you do any mathematics? Not only we can do a lot of mathematics, like the 600 pages in the book, but also we find new mathematics. This is just to give you an idea. You introduce a notion of pair, a set of concrete points x and a set of observable s, and any relation between them. And then define a lot of operators, interior and closure, on points, and saturation for formal opens and reduction for formal closed on the set of observables. And you can see that they satisfy a very strict logical duality, symmetry, and isomorphism between where the double arrow is. All of this is very elementary, but as far as I was able to check, it was never mentioned in any written reference before I discovered this in the 90s, 96 or 99, beginning 95. This, in my opinion, is because if you have law of excluded middle, then closure is the negation of interior. Closed is the opposite of open set. If you have a power set axiom, then the second set is useless because opens form a set, because you don't distinguish between opens that typically are a collection and sets. And so opens, it is useless to keep the second set S, which is the base, the index for the base of topology, if you have a topology. So that's why the set S was never considered before, and that's it. So the cat was going to visit us. Yes, he's there. Hope it remains quiet. So this is an example of math coming out from this very minimalist framework. And it is, in my opinion, enough to reject the claim that the classical paradigm is the only possible mathematics because it is the absolute truth. It is quite possible to have a different mathematics out of the classical paradigm. But let's go on. Let's come to discrete and continuous. I remember some paradigm changes. The first was the discovery of irrational, in my opinion, of course. The first was the discovery of irrational numbers, and with Pythagoras. Then 3 centuries to pass from everything is a number to everything is a geometrical entity in Euclid. Euclid was, in a sense, the universal language to express all the mathematics of those times. And then bit by bit, so much later, we have analytical geometry where you need a symbolic expression. That's the big change. And then you have infinitesimal analysis, and then the development of mathematics, and so on. Then, of course, we have another paradigm changes with Cantor set theory mostly, but let's before look at another aspect now, namely, all of these speak about points, but points do not exist in nature. While you can say that an interval exists in nature because you can say by experiments when something is inside a certain interval, you could say that point does not exist in nature. A typical example is our vision. When we look at anything, we assume that reality is continuous. We assume that what we see can be divided, can be halved as many times as we wish. But this is an idealization because the input in our brain is really a remarkable organ, incredibly complex. The input in our brain is discrete. The continuity of vision is added. It's a software addition. In our brain, there is working on the inputs, and then we see. Yesterday, I went to get a new pair of glasses that I don't have on, and I realized in a few minutes how strong our brain is when it deals with visual inputs. At first, I could not see anything. After half an hour, it was crystal clear because the brain just accustomed very quickly, by the way. So this is an example. So we want to keep this. What is the difference between abstraction and idealization? Idealization, Hilbert mentions it several times in his On the Infinite and also other papers. Typical example, we just consider that, is the complex numbers. Complex numbers are an idealization. They do not exist in nature. And what is the reason for introducing the idealization of real numbers is that you can get the fundamental theorem of algebra. All polynomials have a solution, have a zero. This is impossible with real numbers. So you invent a way to be able to, you invent a simpler theory with respect to real numbers, in a sense, simpler with respect to being zero with respect to polynomials having a zero, because you have the fundamental theorem of algebra and so on. And the role of ZFC, axiomatic set theory, is to deal with actual infinite as an ideal entity. It helps to simplify the treatment of infinity. The problem is that with complex numbers, you are allowed to introduce complex numbers because, as you can prove with the Argand-Gauss plane, they are conservative over real numbers. Conservative means that what you obtain working with complex number does not go against what you had, does not add even anything on what you had about real numbers. Again, continuous vision must be conservative. You cannot introduce by software work in your brain something that does not correspond to what you can touch, for instance. If your eyes say there is an object there, it must be there. You only add something to obtain stability of the image and things like that, or simplify somehow the image, even if it looks very complex in our mathematization of it. Actually, it is simpler, because imagine if we had a vision with 2-3 million pixels all the time. It would be crazy. It would be almost impossible to see things. So the idealization is to simplify the theory. Abstraction is forget some information to simplify manipulation of objects, and it is justified by application. Idealization is to add some properties or entities to simplify the theory. It is justified by conservativity. The main point is it is not satisfied by consistency. To be able to say that consistency is enough to satisfy an axiomatic theory, you must be Platonic, a Platonist in your ontology, think that everything exists in some universe, and really classical, using classical logic, even in the meta language, even applied to this Platonic universe. So classical in every possible sense. Since we do not accept that, we need to find a way to introduce ideal aspects in mathematics. So they must be justified by conservativity. This is what we see now would take much more time to do in detail, but let us look at it at least intuitively. That is why I talk only about continuum. If you take a tree, as in the picture, and you can consider a path through a node K, also in the picture. A node is one of those points. All nodes form a set that is generated inductively. The rules are, whenever you have a node, you can continue in whatever choice over a certain set. In this case, natural numbers. So lists of natural numbers, namely nodes, form a set, while paths, namely infinitary lists that go on forever, do not form a set. I have no way to generate all of them. If you try to say I have a list, immediately by diagonalization, you can see that you can go out of it. Paths correspond to the Brouwer's notion of choice sequence. If you assume axiom of unique choice, then this amounts to say every path is law-like. That is, every path corresponds to a law, as are real numbers in Bishop. So I do not follow Bishop, and I also do not follow Brouwer, but I reconstruct the notion of choice sequence as a path. A path is more geometrical than choice sequence, but I don't know if we have time to see details. But I clearly keep it distinct from the notion, from effective notion, because a path is infinitary. So in this way, we can have, if we have axiom of unique choice, then since in a path every node has a unique successor, if axiom of unique choice is valid, then we automatically have the instructions to obtain the successor, and so the path becomes law-like. So that's the good reason, intuitive, visually clear reason why we don't want axiom of unique choice. Okay, let's see. So in this way, you must keep this picture in mind from now on, distinguishing very carefully from nodes that are finite things and paths that are infinitary things.
Yeah,
So,
Giovanni, can I just ask? So you rule out non-computable
yes.
numbers?
Yes. I am not, I call people who, constructivists that restrict to only computable entities, I call them orthodox constructivists.
Right.
So you do unorthodox.
Okay, so you do accept non-computable.
Yes.
Okay.
Like a subset, I accept even if I cannot list it in any way. So that's another big difference with respect to Martin Löf, Bishop, and also the so-called Russian school, Markov, and many other, where everything was explicitly computable.
In Russia, we call it Leningrad School. You should know.
Leningrad School, okay. Good to know. Okay. So yes, I accept it. And actually, I believe that's very, I am very conscious of that. It was my aim since long ago. I believe our visual intuition is almost at least as important as our mechanical intuition, our intuition about computation. Visual intuition, for instance, just to see how strong it is, think when you look at something and you have to check if a certain line is parallel to another one, and you understand it just by looking with extreme precision. So just a little example showing that we have a strong intuition in our mental potentialities. So yes, it is true. I purposely keep those two. So, and so we come to the main distinction. The main distinction is the computable side is expressed by point-free topology, while the non-computable side is expressed by points. So take the points of most common topological spaces. Real numbers, they do not form a set. Trees, as we just saw, paths do not form a set. Prime ideals of a ring, they do not form a set. All of these do not form a set. So if we want to be constructive, of course, we must preserve all amount of computation as possible. So we will have to give priority to point-free topology, where you have sets. We will see better in a while, and only over point-free topologies, we will build the notion of point to obtain collections obtained by suitable subsets of neighborhoods in a point-free structure. This is, I would say, the main contribution of the book, showing that we can add, on the left here, you have the concrete case where you start from the concrete case where you have a set of points, and then with the suitable method that I try to explain now, we obtain a notion of point-free topology, namely the positive topology of the title, and the notion of ideal points and hence ideal space. This will be our common notion of points. All examples in the mathematical literature are obtained in this way. A way to understand this diagram is to think of Dedekind's definition of real numbers. If you start from the concrete space of rational numbers, then X will be rational number and S will be intervals. And the relation will be the given rational number is inside the given the interval. So if you have such a basic structure, by the way, it is a basic pair in the previous sense, or actually it is a concrete space. I did not give the definition. If we have such a structure, we can move the structure of X into S, the observables, and define some operations that are induced by this movement. And these operations are those that we saw. I don't know if I'm able to go quickly. Yes, sorry. The operations are this J and this A on the right side. They are operators induced by the movement of a subset between one set and the other along the relation. So a very structural definition. So we do that and induce the possible operation on the set S, which was pairs of rational numbers, and we have suitable operations. But if we stay here and then take the notion of, this will be, by the way, sorry, this will be a positive topology, but not the most abstract one. Because if you go back to concrete spaces by the notion of ideal space, you will go back to rational numbers. So we must do what Dedekind did in his notion of cut, Dedekind cut. He observed that a Dedekind cut is produced by a rational number, but there are many Dedekind cuts defined as a bipartition of rational numbers that have no separating point. And these are exactly the new real numbers. And he called that just a section. Section not determined by a rational number. So we must do the same here and move from the notion of induced positive topology to the abstract notion of positive topology, which does not come from a concrete space, does not come from rational numbers, as in the case of Dedekind, from no numbers, from no concrete space. So this is the notion of positive topology. And then we define ideal points over a positive topology. And luckily, but it was, of course, all planned, the paths in the example before are exactly the ideal points over a positive topology defined totally effectively over lists, over nodes. And this is a very strong result, I believe, confirming that our approach is. So at this point, I ask, how long do we go? When do I stop? 10 minutes? 5 minutes?
Well, we don't have a certain time restriction, so you can go for 10 minutes or more. Yeah.
So I'll use 10 minutes. So we quickly see this diagram in more detail, but these are things that it is better to study by yourself in a book. Otherwise, I should be extremely more detailed. So if you start from a basic pair, you have the notion of basic topology. Start using the method just in the previous slide. If you start from a a basic pair has no assumption on the relation. Concrete space has some assumption on the relation between points and observables, enough to say that concrete opens form a topology in the common way, in common sense. By projecting all the structure induced by a concrete space over the set S of observables, we obtain what I call a positive topology, a specific example of positive topology. And we do the same on morphisms, but we don't talk about it now. And but just to, in the same way, the notion of singleton, if we project it on the formal side, we obtain that diamond X or diamond D, and that will be an ideal point. And then all of this must be abstracted to the case of non-representable point-free structures. This will be the abstract notion, basic topology. You just read it, a set with two operations. The novelty is this link between saturation and reduction, which is expressible by using the notion of overlap. That funny new symbol means the two subsets overlap over some element. It's different from being non-empty because we are intuitionistic. And in this way, we have a point-free notion of open expressed by script A and closed expressed by script J. A positive topology is adding convergence. In the drawing of the tree, convergence guarantees that when you go up, you don't bifurcate. That's exactly the reason for this addition of convergence. You only have one way to go on. And a continuous relation, we jump. And an ideal point is a convergent formal closed subset, or in detail, it is a subset of approximations or observables. It is inhabited. It is filtering, namely if two approximations, if two observables are approximations of a certain ideal point, then there is a better one that is of both, that is also a which are also approximations of the same ideal point. Then if you have an approximation covered by a subset of neighborhoods, then one of those will be in the ideal point. And if you have an approximation of an ideal point that are all contained in a subset of neighborhoods, then we say that that approximation is compatible with that subset. This positivity relation is very strong, very novel, and it allows for the definition of formal closed. In particular, it allows to say that you obtain a branch in the example of trees. To check that the point-free topology is really effective, I show you only the axioms to say that the cover, namely the script A operator, and the positivity, namely the script J operator, are really effective. We can generate them in a very effective way by induction and by respectively co-induction. To be able to say that this define a proposition, namely, and hence a relation, even if infinitary, cover and positivity, we need to assume something a little bit stronger than what I said before, namely the possibility to define a proposition in using a very elementary induction and co-induction on a situation like axiom sets. Okay, so this, since if you have this definition, you can see that starting from any axiom set, you have a positive topology and a basic topology. And so the notion is extremely general. So the picture now is point-free topology will be real mathematics with computational content. That will be point-free topology. In the book, we have a new notion of point-free topology that I call positive topology, and because everything is positive. And it allows to define everything, including, for instance, closed subsets, in a positive way, not by negation. Ideal mathematics will be ideal points and ideal spaces over real mathematics, namely positive topologies and similar. Idealization is used only as the last step. And one can check in all the examples. I have no meta theorem, of course, but in all examples, the last one that we understood by some result of Tatsuji Kawai is that you can do that in the case of real numbers, that you can add ideal points only at the very last step. Without needing to make quotients or subspaces or anything. So the general claim now becomes all useful mathematics for applications, understood, all useful mathematics is expressible via concrete and ideal spaces. Mathematics that is used in applications will be real mathematics obtained by abstraction, and hence it will be point-free topology. Ideal mathematics will be useful for us to express our intuition, for instance, infinitary path, our visual intuition, because it is like a continuous vision produced by our mental constructions, like arbitrary paths. So all of these, I only have 3 slides here that I leave for you to consider. We can discuss about it with questions. Anyway, very recently, some 9 years ago, time flies, I realized that one could say that my proposal of everything constructed, human product, constructed from the bottom, and so on, minimalist in the assumptions, and so on, is just could form a new paradigm in the sense of Kuhn, the book, The Structure of Scientific Revolutions. I'm not expert of this, but it is useful to express what I aim. One question, I am fully aware that there is one question, is it possible to have different paradigms in mathematics? My answer is yes. I believe there have been many. I hinted at a couple at the beginning. Note that the paradigm given by Euclid was a paradigm. And in fact, there was opposition. Archimedes did not accept it. He did not follow the Euclidean paradigm, and we know by his own words. We were lucky enough, not we, I was not there, that archaeologists found a letter by Archimedes in 1908, I believe in Istanbul, where he explains his method and says clearly, I do not follow the common way, namely Euclid. The latest example of paradigm is set theory, the introduction of set theory. It's a huge change. And part of the paradigm of set theory is that it is the only possible paradigm. Why? Because they replace truth with consistency. It is difficult to imagine a mathematics that is out of consistency. Some people, some crazy people do it, but it's somehow difficult. So if you say whatever is consistent is part of mathematics, then of course there will be only one mathematics. But if we break that principle and conceive of basic notions such that truth, proof, effective, and so on in a different way, then we can see that there is a different paradigm. One question in my mind is only, is dynamic constructivism, namely the approach I propose, a new paradigm, or is it the refinement of the previous one with sets? So the last two slides are these. On the left, you have the supernatural paradigm, and on the right, the natural paradigm, namely green, what I propose, ecological. So you can see, for instance, math is independent, static, supernatural, while math is constructed, dynamic, and human. Sorry, I moved this. Human. And truth is given, top down, information is acquired, bottom up, and so on. The difference, I like these three. Existence is not explained in a verifiable way because they say consistency proves existence, but we have no way to verify that gives proper existence. Existence here is a cultural product. What does it mean? That the collective mind produces a new notion, a new entity, like what we said about set, and that is the existence of the notion of set. So existence is somehow intrinsically a collective enterprise where each of us, human being, contributes to the existence of a certain notion. Note, this is not different from all other cultural products, like music, even any abstract word, the use of colors, more delicate, but if you think over, interesting, the way we treat in our cultures the relationships between the two genders, male and female. All of these are cultural products, even if we feel them as given. And that's the nice thing about thinking of them as cultural products. By the way, this idea I found in 91 by myself, but I later, some almost 30 years later, I discovered that it was written in a paper in 1947 by a pretty famous anthropologist called Leslie White. And reading that paper, I understood better that you can, thinking of math as a cultural product, you can explain in the same time that it is human produced by humans, and in the same time that you feel it as given, because you feel it as given by the culture where you live. When you study a book, you take it for granted as something describing objectivity. In the same way, objectivity is not like in Frege, Gottlob Frege, he started from objectivity, but he does not define it properly. While here, at least, we can explain what it is. Objectivity is the fact that we expect everybody to agree if we do things in a very careful way with certain standards of methodology and blah, blah, blah. So everything is reduced to human, no need to supernatural notions. And another important point is idealization is not justified by consistency, but by conservativity. And this is about philosophy. And the next. Why it does not go? Okay, mathematics. While the basic notion in set theory is set, as we have seen here, the basic notion, not from the point of view of foundation, but from the point of view of mathematics, is to have points and observables. So you have a basic pair. And the basic pair allows you to have dynamics between the two sets, the one expressed by the funny diagram. Deep structures are hidden here by excess of assumptions, while here, if you take away the strong assumptions, deep structures emerge. Formal systems in the classical paradigm are necessary because otherwise you don't know consistency. Formal systems here are only useful tools. By the way, if you really want to have a formal system for other reasons, like proof assistance or so, you can prove that they are consistent. We have a system called minimalist foundation, which can be proved to be consistent without going against Gödel's second theorem. But we can talk about details if you're interested. So we have seen before that in the classical case, paradigm, there is a distinction between, a debate between what comes first, continuous or discrete. And some people say one, some say the other. And anyway, it's not clear what is the relation between the two. Here, I take a very clear position, perhaps too clear. Some people will find mistakes, but I'm pretty convinced. Discrete comes first, and it corresponds to effectivity, point-free topology. Continuous comes by idealization and comes later. And continuous is the limit of discrete. In the classical paradigm, Brouwer was crazy. He contradicts truth because, of course, he contradicts consistency when truth is considered only as consistency. Like consistency including definitions with no value and so on. Brouwer here is explained deeply. Typical example, the continuity principle. I do not have time now, but you can prove the continuity principle if you give a proper definition of what it means to have a mapping between ideal spaces. Ideal spaces. Here I am a bit over the lines, perhaps. Grothendieck's expectation of toposes forming a more general notion of space never proved, can be proved here by embedding the category of concrete spaces into that of positive topologies. I stop here, and I can go as long as you wish for questions. Thank you very much.
So, Giovanni, thank you a lot for your talk. Now we're ready to question section. So if someone have a question, you can raise your hand by special button. Well, I think I have two questions, one kind of formal and one kind of philosophical. So the first one is on the beginning of your presentation, I think on your slides, you say that the law of excluded middle forces classical identity, saying that the closure of a set equals the complement of the interior of its complement, and that power set axiom makes the formal side redundant. And could you please pinpoint the weakest additional principle under which a positive topology necessarily collapses to the classical point set or local picture, and is there a clean single axiom characterization of that collapse?
I'm not sure I understand. So just let me remark that not only if you have law of excluded middle, you obtain that closure is the same as not it int not, but also the converse. So if in the proper context, like every basic pair, you assume that not closure is equal to interior not, then you can prove the excluded middle. So it's unavoidable to take away the excluded middle if you want to be positive. And something similar with the power set axiom. So once you note this, can you repeat the question you did about positive topologies?
Yes, and the second question.
No. Oh, that was the second question.
Is there any weakest additional principle under which positive topology collapses to the classical point set or local picture?
I don't know. I don't know because what I consider is the most common principles, excluded middle, power set axiom, and axiom of choice. And you need to be able to make the discipline of positive topology to collapse to the standard approach. You must use all the three of them. I do not know if you can weaken these assumptions and still obtain the collapse.
Oh,
I
okay.
don't know.
Thanks. So, and the second questions about the last one, 3 slides, I think. So, as I understand it, it's clearly your natural paradigm replaces truth as given with reliable information acquired. So, what for you is the mathematical surrogate of truth here? Is it probability in a chosen system or conservativity over a computational core or something like invariance under information preserving translations? So, in other words, what is the criterion of objectivity once objectivity is reread as intersubjective consensus?
Sorry, I was trying to go to, okay. Yes, very difficult question. The answer would be, I don't have a ready answer. It's something I believe, and so I can answer very generally. All the attitude I have tried to explain here is based on the fact that nothing is given outside and that all is constructed by us, including the notion of truth. So I don't reject the notion of truth used by classicists in the classical paradigm simply because it's a problem of excluded third. I reject the notion of given truth, absolute truth, as given out of us. Every abstract notion we use is a cultural construction. This I strongly believe. So I don't know if this is a quick and difficult answer, but you could derive everything from this.
Okay, thanks. It seems really interesting to me. So thank you,
It's not
Professor.
easy. It's not easy. It took
Yeah,
me.
yeah.
I would not express myself in this way 20 years ago. It's not something. It took me a while to understand this, and to explain it properly. I probably it would be better in front of a glass of wine or beer, not vodka because I too easily get drunk with vodka. But in a more empathetic situation, I could explain why I am so sensitive to these matters
Okay,
because
thank you.
my own experience or personality,
Of
I don't know,
course.
mixture, lots of things. But in the end, I really believe nothing, no abstract notion is given. It's everything is
Mhm.
constructed. Imagine human beings go extinct. Do you believe that the notion of truth will remain there? No, of course not.
Yeah. So, Professor Andrei, have a question.
Yes, yes, thank you. Yeah, actually, yeah, I have a couple of comments and then more specific
Please.
questions.
Yes.
And first comment exactly that point that you call mathematic cultural product and everything. No, I mean, in one sense, it's easy because it's an artifact, right? Mathematics, like Einstein's theory of relativity, also artifact, right? It made by humans. It doesn't come from God or whatever
Yeah.
directly. So everything of that kind is artifact. But when you say just like any other cultural product, I think we should be a bit more specific. I mean, it depends, of course, what you mean cultural product. Just like think about like a kitchen, right? Cuisine. And of course, there are different cuisines. They share something in common, right? It shouldn't contain a poison, so it should be consumable by human. And still
Yeah.
there is variety, or there are religious beliefs. Again, you may probably generalize in some common feature, but mathematics is a say yes and no. It's still, I think it's really. I actually spent, I may say, all my research life, right, studying kind of cultural difference because I'm more historian than mathematician, historian of mathematics, right? And still, I think when we talk about simple things like arithmetic, the most striking uh, how say anthropological fact, if you like, is that counting was invented in many places. There is no like invention of counting, right? It's there are many archaeological finding documents, and it was right in a sense all the same. And in which sense? Of course, because in the sense that it's all kind of intertranslatable. Of course, people use different system of writing, right? They might, how say, have kind of cultural biases in one way or different way. But arithmetic is still arithmetic. There is a good sense in which, in all these cultural appearances, it's still the same arithmetic, and we can responsibly reconstruct what does it mean the same in that case. You see, and that is something which I would say calls for explanation where it goes from human brain or from world. I wouldn't exclude world. I think even human brain it sits in the world, right? So it's even if you're right calling maybe it's a cultural invention, but it's really reflects something say objective, right? Something that we cannot just choose or change by fiat. It's and that's of course I think remains a problem. So just saying it's cultural artifact, I think somehow you don't really solve the problem. I mean, problem
No, no, of course, of course.
it's still
You
there.
are touching a huge,
Yeah,
huge,
sure.
huge issue. I mentioned just to to explain that I understand what you're saying, think of the example I mentioned before, music and relationship between genders. So in music, it is cultural. We see that many cultures have a different organization of the musical scale, but it is still based on something objectively.
Right.
Like,
Octave is about numbers and it's objective octave, right?
exactly. I meant exactly that. But if you listen to some female singers in India who follow their culture, I don't remember the name, but I have in mind the experience, they are just totally out of our Western 12 notes scale between one note and its double or its half, which is the octave.
Right.
It is just different. So it is a mixture, of course. And also, the more something is connected to our body, to our biology, the more it becomes stable. And in the case of Pythagoras discovering the connection between music and numbers, it is really stable because it deals. It has to do with the oscillation. How do you pronounce?
Yeah. Frequencies, right?
Frequencies.
Yeah, it's actually it's physical also. Yeah, you can
Yes,
explain what is
you may
octave
have
physically.
going like that or doubly as quick, and you
Yeah,
have a note that you understand it's very connected to the previous one.
sure.
And so it has a strong physical
Yeah.
base. And I believe the same for even if it is much more delicate and complex, between sexes. There must be something dealing
Right.
with our biology. Otherwise,
Right.
we would not have a very complex way in our cultures to deal with it. And
Sure.
by the way, in the case of mathematics, it would be very interesting to study from the point of view of history when we got to have essentially only one mathematics, namely the one based on set theory. I don't believe that, and by which process, so to say. It would be very interesting. I don't believe that set theory, as we know, meaning axiomatic set theory with a huge staircase of cardinalities and ordinal numbers and so on, I totally doubt that that is based on our biology. That is based simply on our way to simplify the understanding, our wish to simplify the understanding of actual infinite, and our wish to cover all possible cases, so using consistency and not, and so on. One example I put in the book, consistency is not the criterion. Otherwise, how could you explain that we still don't burn sexually free women or heretics on the public square? We stopped doing that, but it was not contradictory. It was totally consistent.
Yeah, interesting.
Even if awful,
Yeah,
of course.
I come to that in a minute. Just also short historical
Yes.
okay, comment about Archimedes. No, first of all, this palimpsest, it was not actually lost. It was just studied by Heiberg in 1906, first studied, right? And then was long story when it was partly forged and now actually they rediscovered. So it's fascinating. But I think that it's still
So
not quite. I wouldn't say that Archimedes kind of changed paradigm, Euclidean paradigm. I don't think. I think that they what you refer to, right? this probably letter to Eratosthenes where he explains his method. Yeah. It's simply what classically would call analysis. It's just this part, how say, it does not, it is compatible with what Euclid shows us in elements, right? But it's kind of different side of the medal, because Euclid just shows us synthesis. So all these methods they are behind somehow. They are not in this in the elements, right? And Archimedes shows us more this kind of kitchen, how it's what methods work. So it's all I would say Archimedes fully compatible with Euclid as far as epistemic standards are concerned. Yes.
You are more expert than I am on these matters. So I should be careful when I make strong statements.
Okay. But my real question is actually, no. Let's take example of real numbers, right? I really try and better understand what you are. So you are saying that something like Dedekind cuts, right? It's in some very broad sense constructive. So it's not orthodox constructive, certainly, right? Because and it's what actually Hilbert called genetic. So it's somehow right. But then you also thought it's kind of effective. I don't think probably I did not understand because right, if we introduce the Dedekind cuts, we have a lot of uncomputable things, right? So it's not something exactly. No, okay. If you want to call it constructive, then how you would specify? Because it cannot be computable, right? There is no algorithm.
Mm-hmm. So I specify. Perhaps I was too quick. When I say in the end it is effective, I mean the point-free aspect, namely the relation between approximations, what you can do just considering observables or approximations. In the case of real numbers, intervals. When you define a section, what you do is a logical operation. In fact, what corresponds to a section in the framework of positive topology is a subset of observables over the positive topology. And the subset, as I said before, is a proposition. So it's not a computation, but still it has a very clear existence as a predicate, a proposition, something you can express explicitly through words and logic. It's not something totally in the air like Platonic existence or huge cardinalities. It's totally different from
well, but it looks close to what Hilbert had in mind. Okay, he had it should be consistent and just minimal requirement, the consistency, right? Because what is not consistent is something you may say you are not really saying, right?
Okay, yes, this touches a point where you probably, if we meet in February, I would like to discuss this very detailed. The point is, to make it very short, that Hilbert was wrong not in requiring consistency, but in not realizing that his way of understanding consistency is exactly what I call conservativity. Because he used classical logic also in the meta language, and he used completeness of the elementary theory. If you have classical logic in the meta language, completeness that Gödel excluded of the elementary theory, then consistency implies conservativity. It's 3 lines. It's very easy to see. Actually, there is a passage in Hilbert where he says the first and unavoidable condition is to prove consistency, that is, and then after the that is, that in German is nämlich, he gives the definition of conservativity. For him, the two things were the same. This is very unfortunate, because after Hilbert, people understood consistency, and they went on with consistency without realizing that the problem was more deep.
Yeah, thank you.
It's very interesting, I believe.
Yes. Yes, yes, thank you. Thank you so much.
Okay, if someone wants to ask another question, I think, or I also have a question, so I'll ask it real quick if that's okay. So my question is related to the current development of proof assistance, because like going back to the question of paradigms in mathematics, basically right now what we can see with the like interactive theorem proving tools is that we have a few approaches that, I mean, they're constructive, right? But they're also, but they can also be like classical in very specific cases. And in general, we have like a few approaches there that contradict each other, basically, right? Both in technical sense and in mathematical sense. Do you follow this development? Maybe you have any ideas about that, because I think it relates to what you're talking about also.
Yes, it is very connected, and I have been thinking on it for a long time, but I have no familiarity with specific systems. So what I say is very theoretical. There are many things to say. First, mathematics, a tendency of people, of computer scientists, is to accept that mathematics is what mathematicians do, and it is unique. There is only one mathematics, and it is exactly what mathematicians do, including huge cardinals and so on. I strongly disagree from this. And in fact, if mathematics is what you develop in the way I propose in the book, just a proof of what I say, the de Bruijn factor, you know what the Bruijn factor is? Okay, then for other people I explain if they ask. The de Bruijn factor, which usually is 2030 for a paper, a standard mathematical paper, for the mathematics written as I suggest becomes 1. So formalizing the mathematics produced in my sense is almost automatic. It requires no big effort, almost automatic. That could be just a big reason enough to develop my way of doing mathematics. Just this reason would be a good reason to choose for the way I propose. And why is it so? Because if you have very weak assumptions, actually essentially no assumptions at only definitions, most of a proof will consist of undoing definitions. What's the word? There is an English word that now doesn't come to my mind. If you have a definition, you just develop it and see what it means, and you take the pieces, and just from doing that, you obtain the proof in most cases. If you look at any proof in the book, particularly in the first chapters, I was very detailed, but in the same way, the framework is very strong not because of assumptions, but because of correct definitions, that I can give a complete proof in a very few lines, and still they are so close to the machine that you can somehow see the underlying logic almost immediately. I have given an example. If you are interested, I don't remember by heart at which page, but if you write me an email, I can tell you where I give one example of this, showing that the level of accuracy that you have in this way is very close to proper formalization. And proper formalization, then from that point on, it's a matter of computer scientists. I do not know programming languages, so I would have nothing to say about that. But I have a lot to say about the organization of mathematics with very strong assumptions that are very difficult to give to a machine.
Okay, thank you.
So
by the way, sorry, one addition perhaps. By the way, everything started from type theory. Formal topology started in 1984 after I finished to write the booklet Intuitionistic Type Theory by Per Martin-Leff, and I wanted to put it into practice. So I have always been aware of the fact that type theory has been the base of many proof assistants. And so in that sense, and by the way, we changed the name from type theory to minimalist foundation because of some assumptions that I tried to explain. And in that case, the minimalist foundation is even closer to a proof assistant than it was type theory, because we don't have proposition as sets, so logic is different from set theory, and we don't have unlimited assumptions on well-founded sets. And we don't have universes. These are very strong assumptions which make the theory difficult, also for a proof assistant. By the way, similar remarks could be made on univalent foundations, Voevodsky proposal, probably, but I'm not expert enough. I only say that it is a system, not a new philosophy. A new philosophy regarding a specific topic, namely how to instruct a machine. It's not a new paradigm in the sense I was trying to explain.
Okay, yeah, thank you. Thank you for the answer.
So, dear colleague, is there any other answers?
Questions? Yeah.
Oh, yep. Sorry, questions.
Okay, I don't see that anyone else. Alexander, maybe you have a question?
No, thanks.
Okay. Then I think that's all. Thank you for the talk again.
Thank you.
Thank you.
If you have further questions, just write me an email and I will be glad to continue our dialogue. Okay.
Thank you.
Thank you very much.